All right, welcome back after lunch. Hope you enjoyed it. We're going to continue things along with Ihor from Kry10 talking about system information flow analysis. Thank you.
All right. Hi, everyone. So I'm Ihor. I work at Kry10, where we're developing a platform and OS for secure and reliable systems. So this talk is about information flow. And having been in the SEL4 community for a long time, I've worked on a lot of projects. I've heard a lot about information flow and all the different things that it might mean. And I've always been kind of confused about that. And so this is my attempt to try to get a better understanding of what information flow is and kind of the whole concept of that. And hopefully it'll help you all get a better understanding of that too. So at Kry10, we want our systems to provide protection, resilience, and lifecycle management and support. And this talk is going to focus on the protection part, where protection really means security. And it's really about kind of building systems that prevent bad things from happening, prevent attacks from happening. And there's two aspects of that. The first is taking existing systems and hardening them and discovering vulnerabilities and removing the vulnerabilities. And then the other aspect of that is from the ground up designing systems to prevent threats and vulnerabilities from actually existing so that they can't be attacked. And information flow is a critical part of this, right? So a lot of kind of security work involves information flow. So that's what I'm going to talk about. So the rest of this talk, I'm going to introduce or go into more detail about information flow and security. Then I'm going to talk about how it relates to SEL4, and then how we use information flow to design and analyze static systems, and then how we do that with dynamic systems, and finishing off with how we do that at Kry10. So security and information flow. Security is a lot about security policy. So if you want to build a secure system, you need to define a security policy, which says what the system can and can't do, right? What's allowed in the system, what's not allowed in that system. And for a lot of these security policies, information flow is an important part of that. And so when we talk about information flow as part of a security policy, we typically consider our systems as a communication graph. So we've got components that communicate with other components. And then we want to talk about what information flows are there in this system, right, in this kind of communication graph systems. And in particular, when we talk about security policy, we want to say, well, what information flows are allowed in these systems, what's forbidden in these systems, and potentially what flows are required in the system for them to be secure. So I'll give a couple of examples of what I mean with this. So this is a classic example where information flow is used with clearance levels, where we've got a bunch of different levels that information and components in the system can be at. We've got, at the lowest level unclassified, and then goes up to top secret. And there's some rules about how information can flow in these systems, right? So we can have information flowing from unclassified up into more privileged or more classified levels. But we don't want information to flow down. So if something has top secret information, we don't want that to flow down into the unclassified levels. So an example of a system that might implement this is something that takes some various inputs and collates the data and then analyzes the data and then provides it as kind of a report somewhere, right? So if the data comes in at different levels, like unclassified and secret, as it goes up, it becomes more and more classified, right? So it becomes a kind of higher and higher security. So we want the information to flow kind of in that way in the system. And what we don't want is for something that's become secret to suddenly go into a logger that's at a lower level, right? So the policy would specify that information flows this way, but this would not be allowed, and we would be able to detect that. Another example is private or confidential data in a system. So we have some GPS that's tracking people, for example, and collecting this data, and then aggregating that data and making it available over a network through a query interface. And what we don't want in this system to happen is that the raw kind of confidential data gets exfiltrated directly through the network. So for example, if some malicious code is running in this tracking data component, we don't want it to be able to exfiltrate that data somewhere else without going through these components and having to actually filter it. So we don't want that red arrow to happen. Other example is encrypted data. So we might have some patient data, and when we store it on secondary storage, make it persistent, we want to make sure that it's always encrypted, right? So we want the data always to flow through this encryption component. And then we don't want kind of this patient data component, which if it ever gets compromised or is malicious, for example, to be able to directly write that data to storage for someone else to read. Sanitized input. So if we get kind of input coming in over a CAN bus, we want to sanitize that input before we send it to components that actually process that data. Because it's untrusted input, we don't know if it's going to cause problems with these components that use it. Again, we don't want data to be able to flow directly from the input to the components that use it without sanitizing it first. Another example, multi-tenant systems where we have different services belonging to different tenants, belonging to different companies. We want them to be isolated from each other. We don't want data to flow between the tenants, for example. So these are all examples where we're talking about information flow in a system, in a kind of system that's composed as a graph, and our security policy relies on information not flowing particular ways or always flowing in particular ways. So these are kind of some informal examples of why information flow is interesting from a security point of view. So if you kind of do some research and look up information flow, you'll find that a lot of work has actually been done in the field in defining what information flow is and how you can use it and so on. So I did that. Turns out, you kind of get these definitions of security models, right? And information flow as a security model. And that combines a whole bunch of different things. It combines a formal model of what information flow is, and that includes what is the information, what are these components in these graphs, for example, what can they do, how can they send things across to each other, and so on. So defines all of that, various properties that you can have in these systems, policies in the system, so what kind of communication is allowed. So I showed you in the first example that you can have communication that goes up the levels and not down the levels, for example. Different mechanisms, so how do you actually implement mechanisms that enforce various information flow policies and prevent information from flowing in the ways that it's not allowed to. Different ways of analyzing systems to ensure that they're actually doing the right thing and so on. And then different kinds of assurances, what kind of levels of assurance can you get that your system's doing the right thing. So there's a lot of research that's kind of developing these models around information flow. So some examples of these are multi-level security, which is kind of the basic information flow model that people talk about, which is that kind of, having different clearance levels and having rules about how information can flow between the clearance levels. So for example, no write down and no read up policy, which is, if you're at a high level, you can't write down to lower levels. And if you're at a lower level, you can't read from higher levels. And there's kind of more formalizations of those. There's a confidentiality version of that, an integrity version of that. There's MILS, which really focuses on more of the mechanism for providing the separation between these components so that information by default doesn't flow between them unless you've created actual channels between them. So it talks a lot, formalizes that, talks about the mechanisms for that, leaves out a lot of the flow policy, so what kind of flows are actually allowed or not allowed, and it's up to people who are designing or building systems with MILS to define those policies. There's been a lot of work on formal models of separation, so there's non-interference, which talks about traces of executions of systems and how actions of what, if they have two different categories, high and low, how the actions of a high category can't affect the traces of a low category, and so there's no interference between those two. There's a different version of that, which is GWV separation, which talks about the allowed communication between memory segments. And then there's a lot of work that kind of looks at these two models and talks about, are they the same, are they different? And then there's work that looks at kind of these separation models and the MLS models and talks about, are they the same, are they different, and so on. And that does a lot of formalization, a lot of math, a lot of formal methods and stuff like that. There's access control models that you kind of use to potentially implement all of these. One that's kind of familiar in our community is the Take Grant access control model, where you can grant permissions to other components to do things and how that affects potential information flow. And then there's kind of, if you're considering your system as a graph of kind of connections, then you can do a whole bunch of graph analysis on that to determine kind of how information is flowing in the system. A lot of these models are really strong. So what that means is a strong model will reject a lot of systems as insecure, right? So there's only a small number of systems that can, fulfill the models, can be considered secure according to these models. And my experience is that a lot of times these are too strong for what we want to do. So a lot of this talk is going to be looking at kind of maybe a less strong model, but focusing a lot more on graph analysis. Okay. But before I get there, I want to talk about information flow and SCL4. So SCL4 has the security proofs. So we've got, kind of the implementation proofs, and then we've got the security proofs on top of that, in particular, the integrity proof and the confidentiality proof, which are based on a lot of the kind of formal information flow models. So the integrity is based on the take grant model. So that's, or a version of the take grant model, which is what SCL4 implements. And then the confidentiality proof is based on a non-interference model. And so these basically kind of give us evidence and confidence that SCL4 provides these properties of integrity and confidentiality based on these formal models. So that, if you have two components that don't share any resources, don't communicate, then what happens in one component stays in that component and doesn't affect the execution of the other component, for example. One of the things with these SCL4 proofs is that they have limitations, right? So one of the limitations is that you have to use the domain scheduler in the kernel. So the things you're talking about have to be in these separate domains. Which is not the standard way of using SCL4. Most people don't use a domain scheduler. There's limitations on capability transfers. So after you initialize the system, you can't have any capability transfers in the system for the confidentiality results to hold. If you do have, for example, grant rights, then everything kind of gets bundled up into the same domain as the same label. Also, kind of, if you use call, there's an implicit grant there, and so you're implicitly bundling stuff up. And so it really limits the kind of systems that you can reasonably reason about in using these results. Also, you can't have interrupts at user level, and that also limits kind of the systems you can build. So just kind of using the SCL4 information flow based results is quite restrictive. And so that's another reason why I want to look at, is there something less restrictive that we can do? So the first thing I want to talk about is information flow in static systems. So we've heard a lot about static systems today. These are systems where the resources in the system are allocated at initialization time. So what processes or components you have, what communication channels you have, what memory accesses you have, and so on. And they're not expected to change at runtime. So the system is going to have the same structure, the same system architecture, that same graph for the life of the system. And so when we do analysis of the system, we can do the formal analysis using non-interference and so on, using the SCL4, confidentiality, integrity results, and so on, to get a good idea of what the information flow is in these static systems and see whether they fulfill our policy or not. We can also do graph analysis, right? If we take as kind of an assumption that SCL4 does a good job of doing the isolation, and if we define communication channels between components, those are the only communication channels that exist, then we can treat the system as a graph and do graph analysis and see, does information flow from A to B? Yes, is that allowed by the policy? Yes, then it's okay. If that's not allowed by the policy, then we have a problem. We have to go back and kind of redesign our system. And so we rely on the SCL4 security properties for that. And we've done a bunch of these kind of analyses in a bunch of the DARPA projects. We've done this kind of graph analysis to check whether certain security properties hold in our system. The problem is that static systems can be too limiting. right? You've got the same system running forever at the same time. Especially at Kry10, we're interested in more dynamic systems. So you saw Matt's talk today. It was all about, how do we support dynamic systems? We want to build systems where we can update things, where we can restart components, where we can change the architecture of the system as the system kind of develops and evolves over time. So we want a dynamic system. And this is basically, in contrast to the static systems, is a system that can change over time, right? So you set the system up, and as it runs, the architecture, the software architecture of the system is going to change. That graph of the communication between components is going to change over time. So I've invented 3 different categories of, I say invented, I've made up 3 different categories of dynamic systems. So I call them the semi-static systems, the semi-dynamic systems, and then the fully dynamic systems. So I'll go over each of those and provide some examples. So semi-static systems are essentially systems where the software architecture is static. It doesn't change over time. But what can happen in these systems is that you might be able to turn off and restart components and restart connections, but they'll still have the same architecture, right? So for example, is anything happening here? Oh yeah, back, there it is. So one of the sensors drivers goes down or needs to be updated for whatever reason, and we do that. And eventually the architecture is still the same. So for these kind of systems, if we want to do information flow analysis on them, we can treat them as a graph, and we can apply the same methods we have for analyzing static systems, right? So we can do static graph analysis on them. The challenge there is that we have this component and connection restart, and so we need to ensure that the flow doesn't change, right? So the flow is the same before the restart and after the restart. That the restarted components have the same resources, so they have the same connections, for example. They have the same kinds of memory access and so on, that those don't change. That the restarted connections connect the same components. You don't suddenly have connections to other components. And all those 3 basically are saying, that after we make changes, after we stop a component, restart a component, we're back at basically the same static system as we were before, right? So if we do the static analysis initially and we guarantee, that restarting components doesn't change that static graph, then the result still holds for the information flow, whether a system is secure or not. The big challenge then is to make sure that the system state during the restart, when the component goes down and comes back up, doesn't violate the policy. Matt's presented a whole bunch of work on some of the complexities of stopping components, restarting components, and so on. We've got semi-dynamic systems. So this is kind of systems where you can treat the system as a sequence of static systems. So we have a particular system, and then at some point in time, we kind of tear it down and set up a new system which has a different static architecture. And these are known, right? So kind of if we want to analyze these kind of systems, we basically know the previous architecture, and we need to know what the new architecture is that we're switching in, and then we need to analyze both of those, right? So we need to make sure that the original architecture fulfills whatever security policy we have, and then we need to make sure that the new architecture also fulfills whatever security policy we have. And so we can analyze these using our, for example, graph analysis or other static techniques. And then we need to do some kind of admission check. So if we want to start up a new architecture, we need to check whether it actually fulfills the policy. And this can be done offline. You can check it offline and then include some kind of certificate stating that this new architecture is okay, or you can do it online when you're starting it. So a typical example of when you might do this is a system update. So you've got a system and you want to update it to, like I had in the example, kind of add some new components to it. So we've got kind of a basic system here, and we want to update it to include an encrypted tunnel before traffic goes out in the network, and we want to add a UI to it, right? So we do that, and we have updated the system. And so when we're doing this update, we want to check whether the new system fulfills the security policy or not. So one of the challenges there is that we need to ensure that the system between these kind of architecture switches doesn't violate the policy. And this is a lot like doing system initialization. because we're essentially reinitializing the system. So if we can provide guarantees that our initial system initialization is okay until we actually have the whole system running, then we can apply the same kind of approaches when we're switching architectures. Okay, so these are the challenges. One of the other challenges with this is, how can we check or understand which parts of the system are actually changing and which ones aren't? So if we have two architectures, we can essentially take a diff of those and find out what's changed or not, and then try to only update the changed things. But that changes a bunch of the story as well. It's no longer, like a system in it. It becomes a lot more complicated. And this is another thing that Matt was talking about, is, how do you build that functionality such that you can verify it, such that you can guarantee that when you're doing this switch, it does the right things, and it actually creates that new architecture. So the last category is fully dynamic systems. So here you can imagine you have kind of a shell that takes commands, and your commands are things like, start a web server, start a database and connect it, start a mail server and connect it, stop the web server, start some kind of game server and connect it, and so on. So you're kind of arbitrarily developing and extending that system. This is different than the semi-dynamic systems because you don't really know what's going to happen. So you can't pre-analyze a system. You don't know what the new architecture is going to look like because things are just happening dynamically. Some of the challenges with these kind of full dynamic systems is, first of all, whether there's a single controller or decentralized control. Is it a single component in the system that can start and stop arbitrary things? Or does any component in the system potentially have the capabilities to start and stop things, right? If it's a centralized one, it's a lot easier to monitor that and validate that. Whereas if any component can do it, it becomes a lot harder. So some of the other challenges are just monitoring when new components are created or new connections are created. And this goes back to that kind of controller versus decentralized control question. You want to, in these kind of systems for this kind of analysis, you want to maintain an internal model of what the system graph is. So then you can do kind of this graph-based flow analysis to check whether any policies are being violated when changes are made. And a big challenge is that any components that are going to be creating new components or connections need to be verified as well. So you need to ensure that whenever they make changes, they don't actually violate any of your information flow policies. So we're developing, as I mentioned, Kry10 OS, and we're aiming for that to be a semi-dynamic system. And so in Kry10 OS, the system architecture is defined by a manifest, which essentially tells you what are the components in the systems, what are the allowable connections, and so on. We know this from things like CamKIS and MicroKit and so on. These are specifications of kind of what a system should look like. But some of the dynamic features that Kry10 introduces or adds is being able to restart components, being able to update components, so take a component, replace the code, restart it, and have an updated version of the component. Dynamic connections, so that you can create connections at runtime between components. You don't have to do it all at system init time. And then system updates, so you can basically provide a new manifest to the system and it will reload the necessary components and start up a new system that fulfills the new manifest. And so if we want to do information flow analysis and use this to validate our security policies in Kry10 OS, our approach is to do this kind of static graph analysis based on the manifest description. And then because it's a semi-dynamic system, we see it as a succession of static graphs. So we would do admittance checks. So if the main technique for doing that is our update technique, where we can provide a new manifest and new components and update the system. So we would do admittance tests and checks to see whether the new system fulfills the policy or not, or violates it. Some of the key challenges in that are the root component, which is doing all of this loading and reloading. We need to have assurance that whatever system it builds matches the manifest that it's supposed to be. So we need assurance that it's doing the right thing, and that when we're restarting components, individual components and stuff, that doesn't actually change the graph, right? And so this is a lot of the stuff that, again, Matt was talking about in terms of a verifiable dynamic system needs to support that. We have a message server which is responsible for the dynamic messaging We need to make sure that when it creates connections, they are as expected, they're as we requested, not something else. And then there's kind of the big question, well, what do we need from SCL4? What can we use from SCL4? Can we take advantage still of the confidentiality and integrity proofs and so on? We need to take advantage of the fact that there's isolation, et cetera. So this is, as Matt said, we haven't done this. A lot of that is vaporware. We do have all the dynamic kind of update mechanisms and so on. And doing kind of these admittance checks and stuff is something that's in progress. OK, so that kind of brings me to the end of the talk. Basically, I talked about information flow and how it's part of security. There's a lot of formal work out there, but a lot of that is too strong for a lot of practical systems. We do it already both formally and as graph analysis for static systems, and we're really interested in doing this for dynamic systems, reusing static analysis whenever is possible. And we're doing this at Kry10. Thank you.
Thank you, Ihor.
Yes.
Cool.
I can see how the information flow policies work for the static and the semi-dynamic case that you want to do. But how would they work for the completely dynamic case where you don't even know what components are going to exist? How are you going to describe information flow policies? Like there are no objects that you can say are allowed or not allowed to talk to each other.
So that's a really good point, and that's one of the things I forgot to say is for the fully dynamic systems, I have no idea. Which is why we're targeting the semi-dynamic systems, where we have an idea of how we could do it. I think, so let me rewind that a little bit. In terms of the fully dynamic systems, again, it depends. If you have kind of a centralized controller, then anytime it makes changes, you can update kind of an internal representation of the graph, and then you can analyze that and check whether those changes are OK or not. But if it's fully decentralized and you're just handing out caps, untyped caps to everything, then it's a lot harder.
My question is more, how do you say what is OK if you don't know what exists?
Right, yeah. So you'd have to also have a way of defining the security policy. Yeah.
I mean, you can have a component in the system that updates the policy as it goes along. Like when a new thing is created, it could say, OK, I know how this is supposed to happen.
Yeah, you might also, when you're like dynamically creating new components and connections, also have to dynamically update the security policy with regards to those components, for example. I don't know. That's why we're not doing that.
Any other questions?
So you talk about the creation of new components and connections.
Yeah.
Do we also have a means of saying, like, these specific components and connections can never be removed? Because sometimes the removal of a component or connection might be more important than lots of other things.
So I think that would have to be part of your security policy. So you'd have to have a way of specifying that in your policy that, these components always have to be present. So as I said, like the policy will tell you kind of what flows are allowed, what flows are not allowed, and then what flows are required, right? So kind of part of that required could also be these components must always exist, must always stay there. Yes, Gerwin again.
So following on from that question, there's this tricky in-between part when I change the system setup.
Yeah.
Let's say I have a read connection from component A to component B. The removal of that read connection, that would be a write action, basically. Like there would be information flowing to the component that is only allowed to read.
Yeah.
Or the other way around, but in the wrong direction, basically. So do you have any plans on checking those in-between states?
Not off the top of my head, but do you want to say something? So it depends, but who's that information coming from, right? If that's coming from kind of, your trusted root component, then there's potentially no information there.
But the trusted root component is going to have a trigger for making that action.
Yeah.
And so there's an information flow from whoever requests that
Mm-hmm.
the
Yes.
component here.
Yeah.
That may be an allowed one or not allowed one.
Mm-hmm.
But it's sort of hidden in the
Yeah. Yeah.
removal of the
Yeah.
function.
Yeah. I think that's one of the challenges that we need to work on is, and I mentioned that, right, that the intermediate state, does that intermediate state violate the policy or not? So I think that's one of the big challenges.
Okay, that's all the time we have for questions. All right, thank you, Ihor.
Thanks, everyone.